Welcome to our talk about how to use eye tracking for the individualization of captions. This is a collaboration between ETH Zurich and the University of Stuttgart. Imagine you sit in front of your TV and you want to watch a movie. The movie starts and it is in a foreign language you don't understand. So you turn on the captions to understand what happens. The captions appear at the bottom of the screen, far away from the movie content. While you read the caption, some important action takes place in the movie. You miss it because you were focusing on the bottom of the screen. We refer to this technique as traditional captions. The problem is that due to the distance between text and video content, it is hard to focus on both simultaneously. One idea to reduce the distance between text and video content is to place captions close to the speaker, similar to speech bubbles in a comic. This technique is called speaker following subtitles and has been presented some years ago. It performs an automatic detection of the speaking person and places text close to faces without occluding them. However, in some cases it is hard to predict the text placement of the algorithm. But the main problem with this approach is that it only works with scenes that have visible speakers. Many videos feature off-screen narrations for which this algorithm cannot be applied. In this work, we present an approach that can be applied to all types of videos with captions and that adapts to your individual viewing behavior. So let's assume we know where you're currently looking at on your TV. Then we can adjust the position of a caption to your gaze and integrate the text better into your natural viewing behavior. An eye tracker attached to your TV would provide exactly this information. We call our approach gaze-adaptive captions and develop two techniques: direct captions and salient-sensitive captions. The direct captions follow the simple principle: where you look is where the text will be. This technique ignores the video content and can occlude important areas. Pilot testing revealed that some adjustments are necessary. First, we need to avoid text drift. If we align the top left corner of a caption with the gaze position, one can start reading immediately. However, when you finish reading a text, a new caption will appear at this position, resulting in drifting captions, which might become annoying. We can reduce this effect by aligning the center of a caption with the current gaze position. The second finding is that we need to maintain reading consistency. While you are reading, new text will appear without changing the position. This way you can continue reading, similar to traditional captions. Only if your gaze leaves the caption box and you look elsewhere, a new caption will appear at this new position. As you can see in the video, the text appears centered to the gaze position. However, some of the birds are occluded by the captions. Salient-sensitive captions aim to reduce occlusions with important video content by a displacement of the captions. This displacement has to be calculated live in sync with the gaze. To determine important regions, we recorded a salience map based on a test audience watching the videos with audio. Our salient-sensitive algorithm works as follows. First, we divide the screen into cells and determine for each cell how many gaze points from the test audience would be occluded if we center a caption box there. This way we can create a cost matrix and finally a displacement map that we can use as a lookup where to place captions with less occlusions. The orange cell shows the gaze position. The purple cell shows the displacement. As you can see, this approach has reduced the occlusions with the birds. Similarly, we can create such displacement maps for arbitrary videos, as long as we have information about salient regions in the video. To find out how gaze-adaptive captions influence viewing behavior, we conducted a user study with 54 participants. Half of the study was conducted in Stuttgart, the other half in Zurich. Each participant watched videos with gaze-adaptive and traditional captions. We used short education videos from TED-Ed. All of them had off-screen narration. No audio was presented. The participants had to answer questions after each video, which required them to read the captions and follow the video. For comparison with natural viewing behavior, we recorded the baseline with audio and no captions consisting of 8 participants. This baseline was also used for the displacement of salient sensitive captions. We hypothesized that the average saccade length for traditional captions will be significantly higher than with our gaze-adaptive methods. We could confirm this hypothesis. Guided by previous studies, we assumed that participants would be more efficient in reading text with gaze-adaptive captions and spend more time on other content. Although we found significant differences, the opposite was the case. Since the captions were see-through, we did not differentiate which fixations belonged to text and which fixations were at the content behind the text. With the onset of a new caption, we hypothesized that participants will be significantly faster to fixate it with gaze-adaptive techniques for the first time. We could confirm this hypothesis. With respect to gaze distributions, we hypothesized that gaze-adaptive methods will be closer to natural viewing behavior. By measuring the mean square error between baseline and each technique, we could also confirm this hypothesis. If we look at the heat maps, this becomes more obvious. In the top row, you can see the gaze distribution of the baseline. The bottom row shows the distribution for traditional captions. As you can see, the distributions for direct and salient-sensitive captions look much more similar to natural viewing behavior of the baseline. What are important considerations for using gaze-adaptive captions? First, the target group plays an important role. We found that inexperienced participants preferred the new methods. Participants who watched videos with captions on a regular basis tended to prefer the method they were accustomed to. We also noticed that the displacement of salient-sensitive captions should not become too big. Further experiments are necessary to identify noticeable differences for this parameter. Occlusion of the video content was not as much of a problem as we assumed. However, alternative caption visualizations might help to improve the viewing experience. Some participants also noticed that they perceived the pacing of direct captions as slower and more pleasant to watch. We assume that this might be an effect of our approach to maintain reading consistency. In conclusion, we presented 2 new methods for gaze-adaptive captions we call direct and salient-sensitive captions. They are preferred by inexperienced people and result in gaze distributions that are closer to natural viewing behavior. We also see this as an approach for label placement problems in general. As future work, we plan an application in mixed and virtual reality, where especially information representation in head-up displays poses a big challenge. We further plan to adapt other parameters to personal gaze behavior. For example, the playback speed of videos to help slower readers follow the content better. Thank you for listening to our presentation. You will find further details of our approach in the paper.